Welcome back, everyone. This is Earth and Space Science 101. This is lecture 23. So we're continuing through our chronology of Earth history. We went through the basics of the geologic timescale in the last lecture. So if any of these terms mix you up, just go back and reference the stuff from the beginning of that last lecture as far as how we break down units of time, how we break down time into eons and eras and so on. So in addition to that, in the last lecture, we also covered the Hadean eon, that first 500 million years of Earth history, where all that really integral stuff happened. We got the moon, we got an atmosphere, we obtained our oceans by the end of the Hadean. And so increasingly, more and more, Earth is actually starting to look somewhat similar to our planet today. This sort of circular version of the geologic timescale should help sort of jog your memory a little bit. We're going back through the sort of purple chunk of time here to the beginning of the Archean, and then from this time all the way up to present.
So then that sediment ends up causing a continuation of the coastline where it progrades, or it continues to form and extends itself out into the ocean, in this case, out into the Gulf of Mexico. All right, so that's going to wrap up coastlines and our 2 lectures on oceans. We're going to finish out this lecture by cutting to another little quick field trip. I hope you enjoy it.
All right, so this is Fontainebleau State Park. So we're located just east of the city of Mandeville on the north shore of Lake Pontchartrain. And there are a couple of reasons why I wanted to do a live field trip here in the state park. One of the biggest is this is just a great place to talk about some of the concepts that we already described in the lecture, the concepts of having a depositional style coastline and a submergent coastline, and what that means broadly in South Louisiana. So in any depositional coastline, you have tributaries, rivers and bayous that are bringing sediment into the system. And in our case, in Fontainebleau State Park, those main tributaries are the Tchefuncte River to the west and Cane Bayou to the east. So they're bringing sand and they're bringing sediment into the system that then gets reworked along the lakefront. So then that sediment is moved along the lakefront by that longshore drift that we talked about earlier. And continues to kind of build out and smooth out the coastline.
Okay, once again, we will draw our diagram. It is starting from rest. So it's starting from rest. We're given an acceleration of 9.81 meters per second squared. We are given a distance of 15 meters, and we want to know the time. So when an object falls 15 meters, we expect that object to take 1.75 seconds to fall that distance. So now I've made some testable hypotheses. Let's go and test them. Okay, we just made some predictions. We just predicted that an object would fall 4.9 meters in 1 second. And we made another prediction that it would take an object 1.75 seconds to fall 15 meters. Well, here we are at the biology building, and we're going to test those predictions to show you that, that this works. Okay, here we go. 3, 2, 1. 1.75 seconds exactly.
When you take pictures of the surface of Venus using another type of light, either maybe infrared or X-ray pictures, another wavelength beyond the visible light spectrum, you could see beyond the thick clouds that envelop the entire planet. You can actually see down to the planet's surface. So what we can see is evidence of fracturing, evidence of volcanic activity, and either the planet is still capable of all of that geological activity, or it's just only recently sort of shut down. But we don't see the impact cratering of billions of years of impacts like we do on Mars, and especially not on if you compare it to Mercury. So we think that this planet...
Welcome to General Biology 153. This is our General Biology 2 in our sequence of our 2 introductory biologies. This is the course where you take all the cellular biology you have learned in your previous coursework and use it to understand how whole organisms are put together and how populations function. The origin of the universe is well thought to have begun with the Big Bang. Not a physicist, this is not a physics course. But we do know that if this event occurred, it occurred 10 to 20 billion years ago. Chapter B is the origin of our solar system. And our solar system is just a part of a smaller galaxy that sits over off on the shoulder of the universe. And our solar system is not even at the center of that small galaxy sitting on the shoulder of the universe.
Okay, here I have a turntable, which is intended to have no frictional torque on it. That's not quite true. It's not ideal, but it will mostly isolate me from the outside. So if I stand here on the table, then, and I try to turn, then any counterclockwise rotation to the upper half of my body will be counteracted by a clockwise rotation of the rest of my body. So if I really want to start spinning my body, I'll have to have something else that I can spin in the other direction, like this bicycle tire. So I'm going to spin this bicycle tire counterclockwise, that away, which will make me spin clockwise this away. So here we go. So now, the counterclockwise angular momentum of the bicycle wheel is added to the clockwise rotation of myself, and we still have 0 total angular momentum. Now, if I were to stop the bicycle wheel from rotating, then I would also stop rotating.
Vodka, I should be in the...
Cut the shit, will you? Just cut it! I don't know what you're up to, but I'm gonna tell you it's gonna stop right now.
No, it's not gonna stop. It's gonna go on and on until you face up to your responsibilities.
What responsibilities?
I'm pregnant. I'm gonna have our child.
Alex, that's your choice, honey. That has nothing to do with me.
I just want to be a part of your life.
Oh, this is the way you do it, huh? Showing up at my apartment?
What am I supposed to do? You won't answer my calls. You change your number. I mean, I'm not gonna be ignored, Dan.
Welcome again to Communication and Romantic Relationships. We started today's lesson with a segment from the movie Fatal Attractions because we're going to talk about fatal attractions today. But it's not the type of fatal attractions that you've seen in the movie. It's the type of fatal attractions that are demonstrated in the next few vignettes by some very clever students who go to Southeastern.
Naomi.
Megan, I'm in love.
Yeah?
I met this guy at the pool hall. His name is Matt.
Tell me about him.
When we first saw each other, it was like love at first sight.
Really?
I mean, he kissed my hand. He said he didn't want me to worry about anything. He was gonna just swoop down and take care of everything, and he was going to be my knight in shining armor.
Naomi, what's wrong?
I'm so annoyed.
Why?
Remember that guy that I was telling you about?
Yeah, from the pool hall?
The one that was amazing?
What's wrong with him?
It's like I'm Cinderella and it's 12 o'clock. Something happened. I don't know what, but he's driving me crazy. You know how I love to eat sunflower seeds, right?
Yeah.
Okay, I was about to spit out the shell and he put his hand up to my mouth.
Gross.
Hello and welcome back to Chemistry 107. I thought I'd begin today with a demonstration showing some of the things we discussed last time. In particular, we were talking about the emission of light. Remember, electrons that orbit around nuclei have energetics such that they are capable of interacting with the visible light spectrum. So that's what we're going to look at here in our first example. You'll note I've lit a flame, and the flame is there to provide chemical energy that I can input into a sample. I'm going to begin with a sample of potassium atoms. Actually, this is potassium chloride. Now, it turns out that when I scoop some of this up, I will scoop up some water, some potassium, and some chloride anions. Now, the water and chloride will be chemically excited, of course, when I put them in the flame, but they will emit wavelengths of light that are not visible. But the potassium will emit a wavelength of light that we will see here in a second. I'll put it in the flame, and I'll let the flame heat it up, and then I get, as you note, a characteristic whitish yellow glow into the flame. I'll do that again so you can see the process again. It takes a second for it to heat up, and then I see a characteristic whitish yellow glow, which is an indication that potassium is present in that particular sample.
Tell me a little bit about how you got into consulting people in crisis communication.
I started out as a journalist. I was the guy on the scene of every type of disaster imaginable. And on a daily basis, I saw people make the same mistakes over and over again, whether it was talking to the media, talking to their employees, communicating to any stakeholder, the community. And it was very early in my career when I said, geez, somebody needs to start teaching people how to talk to the media and how to communicate during a crisis. So back in 1994, early 94, I left television news and I essentially started my own business where I travel the world working with leaders in all types of organizations on how to effectively communicate when it hits the fan.
And what are some of the mistakes you see over and over being made?
Geez, how much time do we have? If we look at the constant mistakes, I think we have to look at defining first crisis and defining leadership. For me, as we talk about this, a crisis is any event that affects an organization's reputation and bottom line. I think too many organizations fail to realize the economic impact, the negative economic impact that poor communications or failed communications will have on them.